Hey there, everyone, and welcome to our next episode in our educational series on electricity, brought to you by HET. So in our last episode, we finally got around to talking about electrical potential energy and electrical potential, or voltage, as we also like to call it, which is a measure of the electric potential energy per unit of charge. So in that episode, we used an example of two infinitely large charge plates to divide into the equation surrounding voltage a little bit, and found that since voltage is measured on a per unit of charge basis, the magnitude of the charge doesn't actually matter in our equations because it just cancels out in the equation. So it's really just a function of the strength of the electric field and the distance through which that field is applied. So since our field is constant in this case, it made our equations really easy. And then kind of relating this back to our gravity example, we can say it's very similar as if we were to change this on its side and take, mass out of the equation. So then here, this would kind of be our, electric field equivalent. This would be the acceleration of gravity. This is how, strong our gravitational field is. And then this would be, the distance through which that gravitational field is acting. So here it would be, our, high potential point, and this would be our low potential point. So the reason I'm just kind of recapping this is going to be important when we go into our discussion on batteries, which is what we're going to be getting into today. So like I said, today we're going to be talking about batteries. In specific, we're going to be going over an example of the lithium-ion battery to try to gain an understanding of how these things work. So a battery at its core is just an electrochemical device, which means that it's going to be converting chemical energy into electrical energy. And so to go through this, we're going to be going through the example of the lithium-ion battery, which is the same, battery that's, powering this camera, pretty much all modern mobile electronic devices, even electric vehicles. Okay, so as we start constructing this electric battery, we'll talk about the various components. So we're going to have two electrodes. So we're going to have one over here. One over here. And basically one of these is going to end up being our cathode. And the other side is going to be what's referred to as our anode. So like I said before, batteries are electrochemical devices. Which means that, these batteries are going to be run essentially by chemical reactions. So when we're talking about electrochemical reactions, we're usually talking about redox reactions, which is actually two different half reactions that kind of come together into one reaction where one electron moves from one atom to another. And so what's important, so one side of our half reaction is going to be called our oxidation reaction. The other side is going to be our reduction reaction, hence the name redox. It's kind of a combination of the two names. And at the anode, this is where our oxidation is going to be occurring. The cathode is where our reduction is going to be occurring. Okay. So to help distribute these, the electrons and the charges throughout these reactions, both of these electrodes are going to be attached to what's referred to as like a collector plate. So collector. And these could be composed, of like aluminum, copper, some metal that's good at conducting electrons and charges. Okay, and then all of this is going to be kind of within. I'll get on my green marker for this. Some sort of solvent. In this case, we're going to be using an organic solvent. Dimethyl carbonate, which is denoted as OCH3 2. So this is dimethyl carbonate. Which is an organic solvent because we got carbon. So this is the solvent in which our ions here are going to be dissolved into. So that's a very important, part of these, reactions that are going on, is we're going to need to have ions be able to move from one electrode to the other, but not electrons. So to allow our ions to move back and forth, but keep our electrons going through the wire that's going to be connecting these two electrodes, we're going to have what's referred to as a semi-permeable separator. This is our separator. So this separator is going to allow ions to go back and forth between the electrodes, but our electrons are only going to be able to go by means of this wire here. And so we'll draw our electron here. He's going to be going from our anode to our cathode in this case, although unless we're recharging, and then in that case we would be going the other way. So really, depending on what state, if we're discharging or, running our device, or if we're charging our device, this electron could be going either way across the wire. Okay. So we talked about our solvent, we talked about our two electrodes. So what are our two electrodes going to be made out of? So our anode is going to be composed of graphene or graphite, which is a whole bunch of carbon atoms, kind of laid out in a sheet format. So we're going to have a carbon here, carbon here, carbon here, carbon here, and so on. And this, kind of goes on infinitely. You get the idea. And in between, layers of carbon, so we're just going to kind of denote this C6, just to kind of denote this hexagonal structure, C6. We are going to be having our lithium atoms. So they're atoms at this point. We're not talking about ions yet, but we will be in a minute. So if you look at this, from, a side view, so you might have a lithium ion trapped in there. But then this would just be a whole bunch of, carbon. So this would be like a top-down view of, the graphite structure. This is kind of like a side view. And yeah, and so then we have a bunch of lithium atoms that are kind of trapped in between layers. And then over here at our cathode, we're going to have a whole bunch of cobalt oxide, which is COO2. And then a whole bunch of spaces for our lithium to go, because it's going to get ionized and need to travel over. Okay, so where are these ions that, we were talking about? Well, these ions are going to be dissolved in solution. So our electrolyte in this case is going to be lithium hexafluorophosphate. So our electrolyte, which is basically just a fancy name for a type of salt, which is going to dissolve into ions. Like I said, we're going to be using lithium hexafluoro, so F6 phosphate P, which is going to divide itself into hexafluorophosphate ions, which are going to be negatively charged, or F6 P. He's negative. And then we have our lithium ions, which are positive. So I'll probably draw this guy in blue, but basically throughout this entire, solution, we're at least at the start, we're going to have a whole bunch of lithium ions. And a whole bunch of hexafluorophosphate ions. Okay, so now we've talked about all the different components of this battery. We can start getting into the chemical romance that is the redox reaction driving the electric flow. So as I said before, redox reaction is actually going to be composed of two different half reactions, one occurring at the cathode, one occurring at the anode. So to recap, our cathode here, we have cobalt oxide. And then at the anode here, we got lithium in between different layers of graphite, or we're going to call it, carbon 6, basically. So the cathode side of our reaction, or the reduction side of our redox reaction, we're going to have our solid cobalt oxide. So this little S here denotes that we have solid cobalt oxide. If it doesn't have anything, that just means that it's dissolved in some aqueous solution. So again, here all these lithium ions and hexafluorophosphate ions are going to be dissolved in our dimethyl carbonate. So that is going to turn into lithium cobalt oxide here. So once this electron starts to move over, so he's going to go over there, he's going to end up over here, he's going to combine with a lithium ion, and then we're going to end up with a lithium over here. So this is a positively charged ion, or we're going to combine it with a negatively charged electron, and bang bang boom, we get lithium cobalt oxide, stays neutral. And then, like I said, over at the anode side, we have our lithium atoms over here. They're going to give up an electron, or it's actually the carbon that's giving it that up, but we'll get to that in a minute, which is going to leave a positively charged lithium ion which is going to jump off of our anode here and join its friends in the solution. So this is another interesting thing. So we got electrons that are going to be piling up on our cathode over here. So this is going to kind of become, you know, a net negatively charged. We've got positive ions that are going to be piling up over here. So this is going to be a net positive charge. So all of these positively charged ions are going to be attracted to the negatively charged cathode and go across this separator. And of course, the electrons can't go through. They're here. They have to go through the by means of the wire. The other interesting thing about this is that because we have an increased concentration here of lithium ions compared to this side, these lithium ions are also going to want to flow through here by means of diffusion. All right, so what's driving these, you know, lithium and electron jumping ship in the first place? Well, to get into that, let's put these two half reactions together into our full reaction. So if we were to put these together, we would have, you know, our cobalt oxide plus our lithium ion plus an electron. So again, we're just writing out, you know, our reactants from this side of the cathode reaction. Plus our lithium graphite combination. Which is going to result in the lithium cobalt oxide plus our graphite plus lithium ion plus an electron. Okay. So since we have lithium ions on both sides of the reactants and product sides, we know that these ions don't really participate in this redox reaction at all, so we can basically just cancel those guys out. Same thing with our electrons here. They're not really participating either. They're basically just moving from, you know, one anode or one electrode to the other. They're not actually reacting with anything. And now we're going to take a look at the periodic table to try to come to an understanding of oxidation states. So looking at our periodic table here, we see that lithium is in this group 1A series of elements. And the key thing to remember here is that means that it really wants to give up the one valence electron it has. So if you take chemistry, you know, you can talk about different things called orbitals. So in this first row here, we only have one orbital to worry about. So hydrogen has one what we call valence electron, or one electron that's available for forming bonds in that orbital, but it would really like to have two. Helium already has two. It's what's called one of our noble gases. So all of the elements in this column, you know, helium, neon, argon, and so forth, are all of our noble gases. They have all of their orbitals filled, so they don't really want to form bonds with any other elements. And so usually when you see these elements, they're by themselves. So then we have various rules that kind of determine, you know, what, you know, our different oxidation states are. So all of these group 1 elements, these are always going to be +1, you know, because they want to give up their electron. So once they give up an electron, that means that, you know, their protons and electrons are out of balance, and they are going to have 1 extra proton, which is going to give them that, you know, positive +1 charge. Similar to these group 2 elements, they're going to really want to give up 2 electrons, which will give them +2 charge. And then there's various rules and such that will determine the oxidation states of these other elements. Oxygen is usually -2. There's a few exceptions. And if you want to get into that, there's other videos that you can watch that other people have made that do a really good job explaining those. I can link those in the description. But anyway, so getting to our reaction here and trying to determine what our oxidation states are. So like I said, oxygen is usually going to be -2, and we have 2 of them. So we got -2 charge, or oxidation state, times 2 is going to give us -4. And this is this element, or compound I should say, doesn't have any charge. It's neutral, which means that this cobalt has to have an oxidation state of +4. Okay. Lithium would be +1. Electrons by their nature are -1, but like I said before, we're not worrying about them. So we're going to go over to our lithium graphite mixture over here. So lithium is always going to be +1, which means our carbon over here is going to be a -1,6, right? Because we have 6 of them, so times 6 would give us a -1, which balances that out, giving us a net 0. So then moving over to our product side, again, lithium is always going to be +1. That's just one of the rules. Oxygen is going to be -2. And we have 2 of those, which gives us -4. So 1 minus 4, we got -3, which means that this cobalt is now +3. So over here, our cobalt had, you know, +4 oxidation state. However, it's been reduced, you know, its charge, say, has been reduced, which means it's gained an electron. So over here, you know, looking at our battery here, electron moved over from the anode side, came over here, which get accepted by our cobalt, which really wanted to accept that electron. So it now has accepted that electron, so it has gone from +4 to +3. All right, kind of similarly before, over here on our you know, graphite side, you know, there's no lithium over here. There's really no other element, you know, to offset, you know, the state of this. So this carbon is going to have a 0 state, so he's just neutral. But whereas over here, he was actually sharing an electron that was donated by this lithium atom. So, you know, lithium over here doesn't really want to keep its electron, but carbon doesn't really mind sharing electrons, especially when it's in this, you know, kind of hexagonal state. You know, all 6 of these carbons basically just kind of like pass around that one electron, and it just kind of goes around the ring in circles and circles. But it really would prefer not to do that because it really would like to stay neutral. So therefore that electron is going to go over here where he's not really wanted, over to the cathode side where this cobalt's going to welcome him with open arms and then form this lithium cobalt oxide here. And based on the fact that we have this electron that's flowing over from this anode to this cathode, we know that we have a voltage difference in between the two electrodes. And we can calculate what that voltage is by using tables. So someone at some point was generous enough to run a whole bunch of experiments and try to figure out what the voltage is of a whole bunch of these different half reactions. So here we have our lithium plus graphite reaction plus an electron to give us our lithium graphite mixture has a potential of negative 2.84 volts. This is all within reference to the standard hydrogen electrode, which is denoted as 0. That's just kind of what our reference point is. So all of these are reactions are done at standard conditions, 1 mole concentration, 25 degrees Celsius, 1 atmospheric pressure. And then our, let's see, where is our cathode reaction? Here. So then our cathode reaction here, we have our cobalt oxide plus, so this isn't exactly what, our cathode reaction is, but it is cobalt going from a +4 oxidation state to a +3 oxidation state. So essentially what we're simulating here is cobalt going from, +4 state of charge to a +3 state of charge, which happens at 1.42 volts. Okay, so you'll notice that over here, this is our lithium reaction. So this is actually written backwards of what we actually have written for our battery. And this is just because that, whenever we write these redox reactions in tables, we always write, the electron on the reaction side of the equation. That's just standard nomenclature. But then we see that that has a negative voltage potential. So we know that our cathode half reaction potential, which we are going to draw so cathode equals approximately 1.2 volts. We know that our anode half reaction potential is going to be equal to approximately negative 2.9 volts. We can put these two together to actually figure out what the voltage of the entire cell or battery is. And to do that, so our delta for our cell potential is going to be equal. So we always take the cathode potential minus the anode potential. And we know that this is the cathode because it has a greater or is more positive than this anode. The anode is always going to be the less positive. So theoretically, if we were to go here, we see we have some whole bunch of these half reactions that are positive. So we can actually use two half reactions that are positive compared to our hydrogen electron, as long as we have a difference in between the half potentials. So this could have been, you know, positive 2.9 volts, and in this case then this would have been the cathode, that would have been the anode. All that this is telling us here is that these half reactions are positive, or have a positive voltage compared to our hydrogen electron here, which is just the standard that we use in chemistry. So again, we're going back to our, you know, electric potential example. You know, we're just going from a state of, you know, high potential to low potential. So in our battery, you know, this electron is going from a high potential state to a low potential state. So, you know, this reaction is going to spit out an electron at a very negative voltage and electrons. So here, you know, positively charged particles like to go from, you know, positive states to negative states. Electrons are the opposite. You know, electrons like to go from negative states to positive states. So our electron is going to go from this, you know, negative voltage up to this positive voltage, which is going to complete, you know, the redox reaction that we see here. So combining everything, putting our cathode and our anode reduction and oxidation reactions together, we get a cell potential of approximately 4.1 volts. Okay, so that pretty much wraps up this, you know, video on batteries. Again, the important thing to remember here is that we have, you know, this reaction is going to spit out, you know, electron at, you know, a negative voltage. This reaction is going to want to accept an electron, you know, at, you know, a higher voltage. So electrons want to move from, you know, the low voltage state to the high voltage state, which is what we see in our battery here. You know, lithium really wants to give up this electron. Cobalt really wants to accept this electron. So this electron's got potential, goes over here. Thanks, and I'll see you guys in the next video.